So we're going to discuss the beginning of chapter 4 on what are called digital signatures. So this is a little bit different from the problem of encryption. With encryption, you want to encode or encrypt a message, send it to someone, and they have to be able to, you want to create a public key crypto system so anyone can send you a message. The message is transmitted encrypted, but only you know how to decrypt or decipher the message. So we saw two public key crypto systems. RSA is one, and El Gamal is the other. But here we deal with a different problem, which is if you're expecting a message, a document from someone, and you get sent a document, how do you know it's really from the person who's supposed to send it to you? So we would like some way that if you're sending a message, you can sign it. And because your signature is on it in some digital encrypted way, the person who receives the message can know for sure that it was you who sent the message and no one else. So this is the problem of what are called digital signatures. And in this short chapter, there are two digital signature methods discussed. One is based on the RSA crypto system. The other is based on the El Gamal crypto system. But we're only going to talk about the RSA crypto system method, just so you have an example of a digital signature algorithm. So the general idea is the following. There is some some digital document to be signed. Maybe it's encrypted, maybe it's not, but in any case, there is some document and you want to sign it so the person who receives it, or anyone who receives it, can know it's from you. Right? If a message is sent to Chase Manhattan Bank and says, deposit $100 million to my bank account in the Cayman Islands, and it's from someone who has $100 million that can be withdrawn and deposited, the bank needs to know that the document was really sent by the person who has the authority to transfer the money. And so the document has to be signed, and signed in a way that only the sender is able to sign the document, but there's a public key that enables anyone to figure out whether that is indeed the person who signed the document or not, whether it's a valid signature on the document. So there's some digital document to be signed, and we need a signing algorithm. There is some method, some method to sign the document. And that's going to be a secret method. The person signing the document can sign it, and no one else can duplicate that person's signature. So there's some private key, which only the signer has. We'll call it capital K, PRI for private. So this document is signed by the signer, and what comes out is the document with this digital signature. Or let's say the digital signature is separate from the document. So we'll call that DC. So the document comes in, and if you're the person who needs to sign it, you sign it in some secret way. You know how you signed it, but no one else knows how you signed it. And then it's sent off. And the receiver, what's coming in are probably two documents, the original document D and the signature. So the person who receives the document and the signature needs to know for sure who sent the document, who signed it. So there has to be some verification algorithm. So the person, anyone who receives this digital signature can check whether it really came from the person it's supposed to have come from. So there's some public key which anyone can use, given a document, or K, the public key, and you take the signature, you take the digital signature, you apply this public key, and what comes out are one of two possible results. True if D is really signed by the person who's supposed to have signed it with the private key, and false otherwise. So you're sent a document and you need to know it's really from the person who's supposed to be sending it. So along with the document comes the digital signature. You take the digital signature, you apply some public key to that, and it gives you an answer, true or false. It's true if the document is from the person who's supposed to be from, and it's false otherwise. So this is the outline of how a digital signature scheme works. The question is, how do you do it? What is a method to create a digital signature algorithm? And the very simple one, or simple after we know RSA, is what's discussed in section 4.2, which is the digital signature, the RSA digital signature method. So you remember that RSA was based on the difficulty of factoring an integer. You take an integer, which is a product of two primes, you multiply, and you try and factor it. If you're given two primes, it's easy to multiply. But if you're given the product, it's very hard to factor. That's the crux, the secret, or if you like. That's what makes RSA an effective public key crypto system. And we're going to vary it slightly to create a public key digital signature. So suppose Samantha, that's the name of choice in this section, needs to sign a document to confirm that she's really the person sending the document. So what Samantha does is take two large primes, P and Q, and multiplies them. So she gets a number N, which is P times Q. She's going to publish the number N, but she's not going to tell anyone what the factors are. And we know that phi of N, the Euler phi function, which is phi of PQ, is P minus 1, Q minus 1. That's what we used many times. And we're going to choose integers D and E such that D times E is congruent to 1 mod P minus 1, Q minus 1. That is, if we take a number D, which is relatively prime to P minus 1, Q minus 1, we will, just by the reverse Euclidean algorithm, if you've seen many times, that's just one way. You can find the number E such that D times E is congruent to 1 modulo P minus 1, Q minus 1. And in this setup, D is what we're going to call the signing exponent. And E is going to be the verification exponent. So just to make everything as clear as I can, Samantha takes two large primes, P and Q, multiplies them together and gets this number, capital E. Then Samantha chooses an integer E such that E is relatively prime to P minus 1, Q minus 1. And if that's the case, then there's a number D such that D times E is congruent to 1 mod P minus 1, Q minus 1. And Samantha publishes to the world the number N and the number E. So everyone knows what capital N is, and everyone knows what E is. And Samantha signs a document in the following way. So given a document D, which is a number, right? We've converted everything to integers. So given a document D, some big number, Samantha signs it by computing D, capital D, to her little secret number D, mod Q minus 1, Q minus 1. So given a document capital D, Samantha knows her number little d, that's her private key. She raises the message to the deep power, reduces it mod P minus 1, Q minus 1, and that's the number S. So Samantha transmits her signature S along with the document D. What happens when you receive the message? Or in this section, Samantha is sending everything to Victor. So what Samantha is sending is the message D, the document, and her signature S. And Victor needs to know whether it's really Samantha who's sending the document. So what Victor does, and remember, what was made public to the world was the pair N and E. So what Victor does to verify the signature computes D to the power E mod N. And what happens? Well, computes S to the power E mod N. So Victor has received the signature S from Samantha or from someone. He computes S to the power E. What is S to the power E? Well, S was congruent to D to the power little d mod P minus 1, Q minus 1, which is N. Sorry. Made a mistake. Let me just go back and make this correct. So Samantha's private secret way to create a signature is she takes the document D, raises it to her private key little d, modulo N. N is equal to PQ. not P minus 1, P minus 1. So Samantha takes the document, that number, raises it to the power little d and reduces it mod. And Samantha sends the document along with her signature, encrypted. How does Victor verify that this is really her signature or determine if it is or is not? As follows. Victor takes S and raises it to the power E. E is one of the two numbers that Samantha has made public. She makes public capital N and little e. So you compute S to the E mod N. But S, the way it was encrypted by Samantha, is the document to the power D mod N. So what happens? S to the E is congruent to D to the D to the E, is congruent to D to the D times little e. Remember, D times little e was chosen, so DE is congruent to 1 modulo P minus 1, Q minus 1. So this is D to 1 plus some multiple of P minus 1, Q minus 1 mod N. This is D times D to the P minus 1, Q minus 1 to some K, let's say, mod N, which is PQ. But D to the P minus 1, Q minus 1 is congruent to 1 mod PQ. If D and PQ are relatively prime, which they have to be. This is just 1. So S to the E is just D mod capital N. So let me go through this again so it's not garbled. We need a method to sign a document digitally. So Samantha needs to sign a document, and she's going to send it to Victor. And Victor gets this email with the document, if you like. And he needs to know it's from Samantha, so she also signs it. She sends her signature along with it. And how does she calculate a signature? She wants to do it in such a way that anyone can verify that it really is her signature, but no one can forge her signature, right? No one else can forge her signature or create her signature. So the way you do it is the following. The way Samantha does it is the following. In the RSA digital signature method, you take two large prime numbers, P and Q, and you multiply them, and you call the product capital N. And then you know P and Q. Samantha knows P and Q. So she knows P minus 1, Q minus 1. And she can choose a number E, which is relatively prime to them, to that product. And because E is relatively prime to this, you can solve this linear congruence. You can find the D such that DE is congruent to 1 mod P minus 1 and P minus 1. And what Samantha publishes to the world is this pair, capital N and E. So N, everyone knows N is a product of two primes, but they don't know what two primes they are because they can't factor in. Factoring is impossibly difficult. So Samantha publishes N and E. Now it's time for her to send a document to Victor, and she needs to sign it, so he knows it's really from her. So what Samantha does is that she takes the document D. Again, everything inside is an integer. She raises the document to the power little d, lowercase d, which no one knows. She hasn't told anyone what that is. Reduces it mod capital N, and that number is her signature S. So she transmits her signature along with the document to Victor. Now Victor needs to verify that this really is Samantha's signature. So what does Victor do? Well, he takes S and raises it to the power E. Remember, N and E are the two public numbers that Samantha told to the world. So everyone knows capital N and E. So Victor computes S to the power E mod N. but S was capital D to the lowercase d mod n. So S to the E is d to the d to the e, which is d to the power d times e. But dE is congruent to 1 mod p minus 1 q minus 1. So this is d times d to a power of p minus 1 q minus 1. But by Euler's theorem, this is 1. So we get back d. So when Victor does this calculation, if he obtains d, the document back again, he knows this really was signed by Sam, and he can trust the document. And that is the RSA digital signature scheme. So let me go through the example in the book with what the book likes to think of as small numbers, but for us, they're pretty big numbers. So Samantha chooses 2 primes. Say P equal to 1223 and Q equal to 1987. And then she multiplies them. Capital N is the product, P times Q. So 1223 times 1987 is 2,430,101. And P minus 1, Q minus 1, if you multiply them together, I'm not going to yet. P is 1223, that's 1222. Q is 1987, so Q minus 1 is 1986. And we want to find a number E such that E is relatively prime to this integer. So this product is actually 1222 times 1986. It's 426,892. And I want to choose a number E that is relatively prime to that. And Samantha chooses the number. You can just check on a computer if you want, but that this is really a good choice. E is 948,047. That is, there are almost 2 million numbers that Samantha could choose that are relatively prime to this. She chooses this one. And then she solves the congruence DE, which is D times 948,047, congruent to 1, modulo P minus 1, Q minus 1, 2426892, and finds D equal to 1,051,235. So what Samantha publishes is she lets the whole world know the values of N and E. N is 2,430,101, and E is 948,047. And now she wants to, so Samantha signs document D. And how does she do that? Her signature is the least positive number, which is congruent to D to the D, which is D to the 1,051,235 modulo N. I mean, it's clear from this that you don't want to do this by hand, right? You can't do cryptography by hand. It has to be done with a big computer. And so, for example, if the document D had the number 1,070,777, then S, you don't want to do this by hand, right? You take this number and raise it to this power and reduce it modulo this number, 2.4 million roughly. You get S is equal to 153,337. Again, if you're a computer science major, so you know your way around a computer and you have a computer you can use, you should actually check these numbers. So Samantha transmits our signature, 153,337. And so this goes to Victor. And Victor needs to know that this is really Samantha sending him the message. So what Victor does is he takes S and raises it to the power E mod n. That is, he takes 153,337, raises it to the power E, 948,047. I want to try this at home on a big piece of paper. You actually have to do this calculation. Your computer does the calculation, and you reduce it modulo n, which is this 2,430,101 number. And when you reduce it mod capital N, lo and behold, you get 107,777, which is D. So Victor has verified that this is really Samantha's signature. So he can trust that she had sent the document to him. So that is the thing, that is the RSA digital signature protocol. And I think there are two problems for Tuesday, two homework problems that use this. Last day of class, in quotes, problem sessions is Wednesday. Final exam is Thursday. That's it.